I'm just starting it again. So not to be confused with the trig functions, and not to be confused with the inverse trig functions, arc sine x, arc cosine x, arc tangent x, arc cotangent x, arc secant x, and arc cosecant x. So these are the trig functions. These are the inverse trig functions. We have also 6 hyperbolic functions and their inverses. Hyperbolic, I heard some people call it cinch. I don't know. It's up to you. I call it hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cotangent, hyperbolic secant, and hyperbolic cosecant, and of course their inverses. These are the hyperbolic functions and their inverses. Of course, hyperbolic sine inverse, hyperbolic sine cosine inverse, hyperbolic tangent inverse, hyperbolic cotangent inverse, etc., etc. I messed up my tangent. Hyperbolic cotangent inverse, hyperbolic secant inverse, and hyperbolic cosecant inverse. I am not going to do anything with these. You'll probably encounter maybe one example. You can just copy the formula or use the formula. I will not test you on this. They appear, but they're rare. Of course, again, I'm interested in the top 3, like I was interested here in the top 3 and their derivatives. So, of course, we need to know all trig functions. We need to know at least the inverses and their derivatives, so the trig functions and derivatives, and at least the first 3 inverses and their derivatives. So now let's talk about these hyperbolic functions and what are they. And what's the idea? They are not trig functions, but I see we are using SIN and COS and TAN. Are they trig functions or they're not? Well, they have some behavior that is similar to the trig functions, but they're not trig functions. And then why use the same notation and just throw in there an H? Why not use a different notation? It's because they have some similar behaviors in the sense of identities. We know that sine squared plus cosine squared is 1. Well, sine squared, hyperbolic sine squared by hyperbolic cosine squared equals -1. So they have some similarities. And when it comes to their inverses as well. So I can't think of any other reason why they used, not to confuse us, just to show that there are some similarities in identities. And some graphs, if you want, some similarities in graphs, but they are not trig functions. Okay, so let's see what are they at the core. And at the core, they are combinations of exponential functions, believe it or not. So hyperbolic functions, I'm going to present those 3. Hyperbolic functions are not trig functions, but combos of exponential functions, and mainly, of course, e to the x. Okay, so let's at least define the first 3 and their derivatives. Hyperbolic sine is e to the x minus e to negative x divided by 2. Hyperbolic cosine is the same but with plus. Hyperbolic cosine, e to the x plus e to negative x divided by 2. And hyperbolic tangent is sine over cosine. So hyperbolic tangent, so these are the similarities, will be hyperbolic sine over hyperbolic cosine, of course, e to the x minus e to negative x over e to the x plus e to negative x. And what is hyperbolic cotangent? Of course, 1 over hyperbolic sine. What is, so these are the similarities in identities. What is hyperbolic secant? Of course, 1 over hyperbolic cosine. What is hyperbolic cosecant? Of course, 1 over. So these are the similarities in identities with the trig functions. So graph-wise, let's just graph these three just to have an idea. Hyperbolic sine function is not limited, is not bounded, like sine and cosine, right? Sine is bounded, above by 1, below by -1, we know that, but this one is not. So this is hyperbolic sine. So here's hyperbolic cosine. Something similar to, if you'd like, quadratic function. So this is hyperbolic cosine. And hyperbolic tangent, of course, similar to arctangent, but this one has horizontal asymptotes at -1 and 1. Y equals 1, y equals -1, and it's pretty similar, but different. So this is hyperbolic tangent. And where is it used? I have not been to, embarrassed to say, but I have not been to St. Louis. But one very good example of the arch in St. Louis is a hyperbolic cosine upside down with negative. So this is y equals negative hyperbolic cosine. So if you ever get the chance to visit, you will see the arch is like that. It's a negative hyperbolic cosine. Other applications. I know now everything is underground, but in the past, telephone poles or electrical poles, we still have a lot of electricity above ground. I'm trying to make it as symmetric as possible. So this is another hyperbolic cosine. So they could not fit better, a better function like quadratic or exponential or whatever. It's this combo of two exponential functions when they stretched the wires between two poles. In order to determine the length, they use the hyperbolic cosine. Okay, so when it comes to derivatives, very nice functions. Hyperbolic sine, we can show, if you'd like, because we have the formula and we know how to differentiate this. Let's do at least one. So when I differentiate hyperbolic sine, I put 1/2 in front. It can wait patiently. When I differentiate e to the x, I get e to the x. But again, now we know that when we differentiate e to negative x, we get negative e to negative x, which changes this in positive. And it's plain hyperbolic cosine. The same thing with hyperbolic cosine. You would expect minus. No, for this, in this case, it's hyperbolic sine directly. And of course, hyperbolic tangent prime is hyperbolic square secant. I did note I have to put the I have to put a square after h. It's hyperbolic secant squared. Easy to remember. The same thing with trig functions, except that this one is positive. And now you have all the information you need for the derivatives assessment. Okay. So let's look at a few examples. Here's one. Let's say h of x equals natural log of hyperbolic cosine x. And of course, the question is asking us to find the derivative. So let's find the derivative of this function. So h prime. When I differentiate natural log, I have to have 1 over the function times the inner function prime, which is hyperbolic sine, not negative hyperbolic sine, and this is tangent. So this is hyperbolic tangent x. Any questions? Okay, let's look at f of x, hyperbolic tangent applied to 1 plus e to 2x. So I want to differentiate. And when I differentiate tangent, hyperbolic tangent, I have hyperbolic secant squared of the argument, but now multiplied by, because it's the chain rule, multiplied by the inner function prime. And when I differentiate the inner function, I get 1 prime, which is 0. E to 2x prime is e to 2x multiplied by the inner function prime, because it's not plain x. So I have to multiply by 2. I'm going to put these two in front, and there is nothing else I can do. 2 e to 2x times hyperbolic secant squared applied to 1 plus e to 2x. Any questions? Any questions for me? Is there any particular type of differentiation or type of function that you would like to see again in preparation for your assessment? It's a written assignment before we move on. Any particular type of function? We covered absolutely everything. We covered absolutely all types. There may be slight variations, and I'm sure you'll find them in Web Assign, and you'll bring them to me, to my attention. So that's why I don't mind begging my students. I'm begging you to redo the problems we do in class first. That's the learning process. And then everything else will be, if not a breeze, it will be very easy. So any type of function that you would like me to look at? Any type of differentiation that you may be interested in looking at? Anything? Okay, so I'd like to, and you'll please bring any questions to class. You'll really help me doing that from WebAssign or other examples. Now, the next section, 3.7, deals with rate of change. Rates of change. in different fields. You can say again, rates of change. Again, you've been talking about rates of change from day one, from 2.1. Yes, that's true. We're going to go back to different applications. So the first thing that I would like to look at is a problem on something called Toricelli's law. So I'm going to show you the problem, and we'll read it together. If a tank holds 5,000 gallons of water, which drains from the bottom of the tank in 40 minutes, then Toricelli's law gives the volume V of water remaining in the tank after t minutes between 0 and 40. And this is the function. I'm going to copy the function. So we're given a function that is V. I don't like V. It has to be V of t. 5,000. And in parentheses, n squared, we have 1 minus 1 divided by 40, t squared. And we're given, since the tank empties out in 40 minutes, t is in minutes. And t has, or the function has, domain 0 to 40. Find the rate at which water is draining from the tank. And I'm going to create a table. So they want 5 minutes, 10 minutes, 20 minutes, and 40 minutes. So t, 5, 10, 20, and 40. I will also determine 0. I'm going to put it in front because I like everything in ascending order. Okay, so we're asked again, find the rate at which water is draining from the tank. And then 2 more questions. At what time is the water flowing out the fastest, the slowest, and summarize your findings. We're going to summarize our findings. So how do I determine the rate, and what should I put here? What is this? Say it again.
Did you put in the equation?
But what symbol, or what am I looking for?
Is it v prime of t?
Very good. It's the rate of change. When we talk about the rate of change, we are talking about the derivative. At any point in time, the rate of change is the derivative. Good. So then first I have to find the derivative. So let's find the derivative. So when I differentiate, 5,000 stays outside. I have a function raised to a power. I bring down the power. I subtract 1 from the power, and I get 1. And I multiply by the inner function prime. This is 0. But when I differentiate, I bring down 2. 2 over 40 with minus. 2 over 40 will be 1 over 10 times t. 2 over 40, 1 over 20. 2 divided by 40, 1 over 20 t. Okay, let me see if I can simplify any further. This I don't need. So, yes, I could simplify, put this in front, because I can rearrange the factors the way I want. And I will simplify, and I will have negative 10, and then I have negative 500 t, and in parentheses 1 minus 1 over 40 t squared. So I had 5,000, let me show it on the side, times 2 times 1 over 20. This sign is negative because this is negative, and there is a t in front. So I simplified by 2, and I got 10. And then when I simplified again by 10, I got 500. So this is the final simplified form of the rate of change or the derivative function. I'm going to put this in the graphing calculator to immediately determine these numbers. I'm not going to repeat the calculation. I'm just going to put y equals, I clear what I have. So I have negative 500. X, there is no t in the calculator, left parenthesis. Yes, you could have distributed, there is no need. 1 minus, be careful to put 1 over 40 in parentheses. 1 divided by 40, close the parenthesis, and then t squared, and close another parenthesis. So 1 minus 1 over 40, minus in front, or as I said, you can distribute if you prefer to do that. It will simplify. So 500 divided by 40 is, 25 over 2, 12.5. Okay, so I put it in as is. So I go to second and table, and I want 0, I want 5, I want 10, I want 20, and I want 40. Done. So the first answer, of course, is 0 because t is 0. The second one for 5 is negative 937.5, and you'll tell me the measurement unit. I'm just looking for a second. This will be 40. Why am I not getting all of them negative? Let me check my function. Negative 500x, that's correct. 1 minus 1 over 40, that's correct. Times x squared, that's correct. Because they all should be negative. So second and 0, 5. With 5, yes, this is still 1. I have to start from scratch. I'm not getting, they have to be negative because the volume is decreasing. So the rate of change has to be negative at all times. And even if I further simplify it, this will be negative 500t. Now this is plus. Yeah, okay. So 500 over 40t cubed. So this will be 25 over 2. Okay, so when I have 0, it's definitely 0. When I have 5, when I have 10, and the volume decreases. Let me see, maybe I didn't enter something correctly. Right? So 2, I'm calculating my derivative again, just making sure. So I have 5,000, I brought 2 down, 1 minus 1 over 40, it is t squared. Let me look again. Ah! Got it. Got it, got it, got it. Sorry. The volume decreases. I can't accept a positive answer for the rate. So this is what I copied incorrectly here. There is only a t, the squared is outside, not here. Copied it incorrectly. Okay, I can't get a negative rate, a positive rate. All of a sudden. It's negative at the beginning, and then all of a sudden it starts positive. I said, oops, let's put the brakes on.